So in this section, we've been talking about linear regression, and we talked about first our theoretical model that would happen to be for our population data. And we talked about how to fit the best line or our line of best fit for our sample data. And now we're going to talk about this a little bit more. So we're going to look at our sample data and we're going to try and estimate our population data. But just like everything else we've done, we might want to do confidence intervals and hypothesis tests. Okay, for our slope, which is what we're most interested in regression. So if we looked at our sample data and found this regression line, so this is the same as what we found before, just we have our estimate for our intercept, estimate for our slope. There's always that difference between your sample data and your population data. So this is your estimate from your sample. And this would be your model for the population. But we don't know the population slope, and we don't know the population intercept. Really, we don't even know the population correlation. We could do a little, I think this is rho. Yes, that's rho. So you could do a rho, which is the population correlation, and we estimate that with our sample correlation, R. There's an unknown population variance of errors, and we estimate that with our sample errors, or our mean square error. And this is the variance for the sigma hat squared. The sigma, just a little hat, is called the standard error of the model. You'll just see that term a lot. And it just means basically it's the standard deviation of the errors, basically. Okay, so what we care about here is a confidence interval for our slope. So we can get our slope for the sample, and now we want a confidence interval for the slope for the population. Now for any confidence interval, it follows the form of the R estimate plus or minus a critical value times the standard error of the estimate. So our confidence interval for our slope is going to be this little beta 1 hat, that means our sample slope, plus or minus our critical value t times the standard error of our slope. Now t star is the critical value from a t-curve with n minus 2 degrees of freedom. Let's see what this actually looks like. So this is a regression analysis, what it looks like when it comes straight from the computer. So we'll see a few things here. Notice we have an R squared. We have an R, that's our correlation. We have a standard error. This is your sigma hat, the standard error of the whole model. Let's see, n, that tells you your sample size. And dep var is your dependent variable. So this is the variable y. So it tells you that fat is our y variable. Because we had a study conducted to see if fidgeting or non-exercise activity could help reduce fat gain. So that makes sense that our y variable would be fat gain. Okay. We usually don't have to do too much on this. The computer spits it out. We're not actually going to look at that. Now it does have ANOVA. This is not the ANOVA that we learned about. ANOVA is actually analysis of variance, can be very useful in these in a lot of different situations. And it has different meanings and different applications based on what you're doing. So it's on the computer output. We don't really use it. Okay. We look down here at regression output. You have an intercept, and the line below that is always where it tells you your stuff about your slope. Okay, so for the intercept, it says it's 3.5051. So that means our intercept, or beta 0 with a hat, is 3.5051. And our estimate for the slope is negative 0.0034. So what is the equation for the linear regression line? We'll just be y hat. So we do our intercept, 3.5051. And then this is minus for negative 0.0034x. Okay, what's our estimate for beta 0? So estimate for the intercept. Well, our estimate is just the intercept from the sample. So 3.5051. And our estimate for the slope is our negative 0.0034. So our sample slope is our best estimate for population slope. So this one's intercept, slope. So I'm just going to make a note here of what I've been saying. That our sample intercept is our best estimate of our population intercept. And here our sample slope is our best estimate of our population slope. Let's see, so a study was conducted, so still the same thing, we're just continuing on here. Let's see, what is our estimate for the variance of the errors? Okay, so it's saying, what is our estimate for sigma squared? So our estimate for sigma squared, let's see, remember the standard error, we said that's just sigma hat. So if we square it, we get 0.5476. This is also called our mean square error, if you remember. Now, this is the new part. Find a 95% confidence interval for our slope beta 1 and interpret it. So our formula is you do the intercept from the sample plus or minus a critical point times the standard error for the slope. So our slope estimate was negative 0.0034 plus or minus. Now let's find t star. We want a 95% confidence interval, which means we have 0.025 on either side. We know it needs to come from the t distribution because that's a t star. And remember, I told you the degrees of freedom is n minus 2. So come back up here till you find n. So here's n is 16. So 16 minus 2 equals 14. So we need to go to the t table and we need to find out which t critical point has 0.025 area to the right and 14 degrees of freedom. So looking at my t table, 14 degrees of freedom, 0.025 area to the right, looks like we're at 2.145. So my critical point is 2.145. Now the only thing we haven't talked about yet is the standard error for our slope. The way you do this is it's super easy. You come to your table, look, notice the thing that says standard error. Our slope is always this bottom line. So standard error for the slope is 0.0007. And this gives me the confidence interval of negative 0.0049 to negative 0.0019. To interpret this, the basic interpretation is 95% confident that population slope is between negative 0.0049 and negative 0.0019. So that's just kind of your very basic, simple interpretation. But if you think about what slope means if x goes up by 1, how much does y go up? So let's throw that in there. So we are 95% confident that if x goes up by 1, so if NEA, non-exercise activity, goes up by 1 unit, then fat gain will, instead of going up, let's go down because that's a negative slope, will decrease by, let's say, between 0.0019 and 0.0049 units. So again, if the exercise goes up by 1, we're predicting fat gain will go down by somewhere in there. We don't know exactly what our population slope is, but we're 95% confident it's between those two numbers. So let's switch to a new example now. Let's see, should there be a linear relationship between the amount of candy you eat and the grade you get in this class? So here's a nice little scatter plot of the amount of candy you eat and your grades. And it looks like there's just kind of a, if I was to draw a line in there, it would be kind of a straight line, right? That seems to be what fits it the best. And for this straight line, my slope beta 1 would equal 0. This means that there is not a linear relationship. So if you get a slope of 0, it means there's not a linear relationship. Because if I eat more candy, my grade does not change. If I eat less candy, my grade doesn't change. There's absolutely no relationship. So what you need to remember, the important thing here, is anytime there isn't a linear relationship, the slope is 0. So if it's not a linear relationship, slope is 0. With that in mind, now let's look at what would be the t-test for slope. So we use this t-test for slope if we want to know the value of the population slope. And specifically, we'd be wanting to know, is it positive or negative, or is it really just non-zero? So when we say we want to know the value of the population slope, we're really asking, is there a linear relationship? The assumptions for this is that the errors are independent, normally distributed, and have constant variance. And basically this is beyond the scope of this class. It's way too advanced. So we don't do that. You don't actually have to check that. The null hypothesis is always that our slope is equal to 0, which means that there's no linear relationship. It would look like this, no relationship. The test statistic is your estimate of the slope over standard error of the slope. And really, you don't even need to do this. You can just look at that computer output and write it down. And there are 2 degrees of freedom. What you do have to do for the p-value, which, just like everything else we've done, is the area in the tails. So the computer will go ahead and get your test statistic for you. It'll tell you degrees of freedom, but it does not give you an accurate p-value. Most computer software only gives you a 2-tailed p-value. If you're only interested in one tail, you have to do it on your own, okay, which is why I'm going to teach you how to do it. But if you want to know if the slope is positive or greater than 0, which means that there's a positive linear relationship, you would shade to the right. If you want to know if there's a negative linear relationship, you would shade to the left. And if you just want to say that there is a linear relationship, you're not even concerned if it's positive or negative, you just want to say there is a linear relationship, you would do both tails. Which again, that's what most of the software does. So if you want to test for positive or negative specifically, you have to do the p-value by hand. But that's okay, we have lots of experience doing p-values. Okay, so we're still back to our same example of fidgeting and fat gain. Let's see, we have all of our results here. Number 1 says, predict the mean fat gain for all people that have an NEA level of 101. So first, let's write down the equation of our line. So if I said here, this is our intercept, and slope is the bottom line. So it's 3.5051 minus 0.0034x. Now notice this isn't different than what we've been doing. It's just on here for more practice. So x equals 101. So this is going to be 3.5051 minus 0.0034 times 101, which gives me 3.1617. Now this says predict the mean or average fat gain for all the people that have an NEA level of 101. This one says predict the fat gain for just Johnny, who has an NEA level of 101. Basically, you do the exact same thing. It's still going to be 3.1617. So whether you're predicting it for one person or the average for all the people, you get the same result. Let's see, what is the correlation and what does this tell you? So correlation is just R. This one tells it to me. Don't even really have to do anything. It's just negative 0.779. What does a correlation of negative 0.779 tell us? It's negative, so it has a negative linear relationship. And 0.779, that's fairly close to 1. So we say it's fairly strong, So the points are fairly close to the line. So remember, the closer it is to 1 or negative 1, the closer the points are to the line, the closer your correlation is to 0, that means that the relationship would be very, very weak and they're far from the line. Let's see, now the new stuff. Let's conduct the hypothesis test to determine if there's a linear relationship between NEA and fat gain. So, hypothesis test, we just want to see if there's a linear relationship. They didn't say if it's positive or negative, just if it's linear. So just like every other hypothesis test, we go through all the steps. Let's choose alpha equals 0.05. You need to know your null and alternative hypotheses. The null hypothesis will always be that your slope is 0, meaning that there is no linear relationship. The alternative, in this case, we just want to see if there's a linear relationship. They didn't say if they think it's positive or negative, so we'll just say not equal to 0. And this means then that there is a linear relationship. We don't have to check assumptions on this because it's too advanced for this class, so let's just go straight to our test statistic. So we did give you a formula, but you don't even have to use that. You can just go to slope, t, and slope is negative 4.642. And then, because this is a t-test, okay, because that's what we use for slope, it's a t-test, we need to know degrees of freedom. You don't have to memorize the formula for this either, just come here and notice t, degrees of freedom, equals 14. Now for your p-value, you're going to want the area in both tails because this was a not equal to. So here's my negative 4.642, here's my 4.642. We want the area in both tails. So go back to your t-table. 14 degrees of freedom, we're looking for 4.642, so somewhere off here, so it's less than 0.0005. So less than 0.0005. This side is less than 0.0005, so my p-value is less than, if I add those together, I get 0.001. Now it turns out, I could have just looked up here. The p-value specifically is 0.0004. Okay, and the reason I can just look up there is I did want both tails, so Megastat does give me the correct value. It's just if you only want one value, then you need to do one tail, then you need to do it by hand. You might also notice that it did give me that 95% confidence interval that we did a couple examples ago by hand. The reason I teach you to do it by hand is if you want something that's not a 95% confidence. If you want 99% or 90%, then you can do it by hand. But just like every other hypothesis test, we find our p-value, and then we say, oh, that's a small p-value. It's smaller than alpha. And so we'll reject our null, which means then we have evidence for the alternative, which is that the slope is not 0, or evidence of a linear relationship. And then we can go ahead and write our nice little interpretation. We have extremely strong evidence that there is a linear relationship between NEA and fat gain. Let's try our next example. This one's going to pull together everything that we've learned in the last 3 sections. So a study looked at the number of thousands of steps per day, PA, and the body mass index. You can see here our dependent variable is body mass index, so that's my y, and PA must be my x. So first of all, what variable should be the explanatory variable? Well, you can tell that just by looking here. You always put the y variable here and x here. So that means PA is our explanatory variable. What's the equation for the line? So y hat, do your intercept, 29.5782, plus your slope. Remember, they always put slope here on this bottom line. So minus 0.6547x. What's the correlation? Okay, so come up until you see R, negative 0.385. Now a correlation of negative 0.385 means that this is a negative correlation. So it's a negative linear relationship. And it's a lot closer to 0 than negative 1, so I say this is a fairly weak relationship. Let's see, what's our estimate for our intercept and interpret it? So our estimate for the intercept is this 29.5782. Now to estimate this, this is always if x equals 0, then y equals what? So in our case, this would be if x, or if our physical activity, if our physical activity is 0, or in other words, if you don't walk at all, which because PA is number of thousands of steps, then your expected BMI is 29.5782. I guess this may or may not be practical. There are some people that don't walk, and maybe that is their expected BMI. But remember, our intercept doesn't always have to be very practical, but our slope is. Our slope is what we really care about. So what's our estimate for our slope on this next one? Remember, slope says if x goes up 1, y goes up how much? That's what slope tells us. So our estimate for our slope is the slope coefficient of negative 0.6547. And to interpret it, so if x goes up 1, now x is number of steps in the thousands. So if you walk an additional 1,000 steps per day, we expect your BMI to, let's see, this is a negative, so to go down by 0.6547. On this next one, let's now find a 99% confidence interval for our slope. So 99%, that one's not going to be on the computer output. This one you actually have to know how to do by hand, which is why we teach you how to do it by hand. So if I want a 99%, that'd be 0.99 in the middle and 0.005 on each side. You also need to know degrees of freedom, which is always this n minus 2. But I don't even need to memorize that. I can just come back and look. Oh, notice this one, I actually left those things blank, so you have to do it by hand. So n equals 100. So we have 100 minus 2, which equals 98. Now, technically, we're supposed to round down to use the t-table, so we'll round to 60 for the table. So go to your table, 60 degrees of freedom. And we're looking for 0.005 in the tail. Looks like we're at 2.66. So T star equals 2.66. Okay, so for our formula here, it's always your slope plus or minus your critical point. Now this is our sample slope times the standard error of your sample slope. So our sample slope was, negative 0.6547, and the standard error for it, which we also need, is 0.1583. So negative 0.6547 plus or minus our critical point, 2.66, times our standard error of 0.1583. So this gives me negative 1.07 to negative 0.23. Your simple interpretation is 95% confident population slope is between negative 1.07 and negative 0.23. Okay, but what does this mean as a more practical interpretation? Okay, what your neighbor would actually understand is we are 95% confident that as a person increases by 1,000 steps per day, so x goes up 1, the BMI should decrease between 0.23 and 1.07. So that's what our better interpretation is. Now, as another note here, something that's very important to know is that this is only a prediction. We're kind of predicting how much the BMI should change, or only an association. We can't say cause and effect. So in other words, we're saying if they increase by 1,000 steps per day, we'd kind of predict their BMI should decrease by about that much. We can't actually say it's a cause and effect. We can't say if you increase your steps per day, you will decrease your BMI. And we also can't say that it's the steps, this decrease in the BMI, just that these two things are related and we can make predictions. Finally, we want to conduct a hypothesis test to determine if there's a negative linear relationship. So we want to see if it's a negative linear relationship between the number of steps per day and the body mass index. So alpha equals 0.05. We need to write our hypotheses. We don't have to check our assumptions because it's too complicated for this class. But our hypotheses, the null hypothesis will be that your slope is equal to 0, meaning no linear relationship. The alternative hypothesis is that our slope, now notice they want to see if it's a negative linear relationship. So that means we want to know if we have a negative slope. So we're going to do less than 0. Then we always need a nice test statistic. And for the most part, you can just look at your chart and see what is our test statistic t for our slope. But I left this off to make you actually do it by hand. So our test statistic, if we're doing it by hand, t is equal to our sample slope over the standard error for our slope. So our sample slope, we already looked at these up above. Our slope is 0.6547, standard error 0.1583. So negative 0.6547 over 0.1583 equals negative 4.135. You always need degrees of freedom, which is n minus 2, so in our case, remember we already looked this up in our last part, 98 degrees of freedom. And for our table, we'll round to 60. So for our p-value, here's my negative 4.135. And we only have to worry about shading to the left because this is a negative. Now we'll use symmetry. We'll go to our t-table and just look at positive 4.1. Because of symmetry, the area to the right of a positive would be the same. So we're looking for negative 4 point something. That's going to be somewhere way off here. So we're less than 0.0005. So my p-value is less than 0.0005. No matter what alpha you chose, but we chose 0.05, that p-value is still going to be smaller. So this is a small p-value. We'll reject the null, and that means we have evidence that our slope is less than 0, or a negative linear relationship. Then we say we have, that's a really small p-value, so extremely strong evidence that there is a negative, now let's emphasize that negative part, a negative linear relationship between the number of steps per day and body mass index. And again, we want to write here that this really just means that the number of steps per day is useful for predicting BMI. It doesn't mean that the number of steps per day causes a change in BMI. Let's change this to does not mean. Now, that doesn't mean that it's not causing it, because there could be an actual cause and effect relationship, but we don't know that. As statisticians, all we know is that the number of steps is useful for predicting BMI. We have not proven or shown or even suggested that the number of steps causes a change in BMI. And as another note, the very small p-value, even though we had a really small p-value, it just indicates we're very sure that there's a linear relationship between the two variables. It doesn't actually tell us anything about how strong the linear relationship is. Remember, up above on the previous page, we said our correlation is negative 0.385, and that's a fairly weak relationship. Okay? That means the points aren't really that close to the line, and it also means then that there's a lot of variation between one person to person, and it's not really that closely related to the number of steps per day. There's a lot of other factors going on. So even though we have a really small p-value, that just means we're really sure that there is a linear relationship. It doesn't actually tell us that it's a strong linear relationship.